So what is a vector space? Before we go into that, let's first define what a vector is. A vector is an arrow with length and direction, usually used in physics to represent most forces with magnitude. Now, a vector space is just a collection of these vectors that together share certain properties. Take, for example, what we usually see at school, the Cartesian plane. You can think of it as a two-dimensional vector space, meaning it has two coordinates, an x-coordinate and a y-coordinate. We assume that all vectors start from the origin and extend to their corresponding coordinates. So for this example, 3 and 5. Three-dimensional space, on the other hand, is something we are more familiar with. The world that we are currently living in is represented in three-dimensional space. So in the same sense that two-dimensional space has two coordinates, three-dimensional space has three coordinates, x, y, and z. So a 3D vector space, then, is just a collection of these vectors in three-dimensional space. Formally, a vector space is defined by a set V on which two operations, plus and dot, are defined, called vector addition and scalar multiplication. Vector addition tells us that we can add two vectors together to form another vector. So for example, if we have vectors 2, 2, and -3, 1, and we want to add them up, the x-coordinate of our sum is just the sum of their x-coordinates. In this case, the x-coordinate of our sum is 2 plus -3, which is -1. The same goes for our y-coordinate. 2 plus 1 is just 3, so our y-coordinate is 3. Scalar multiplication, on the other hand, allows us to multiply any vector with scalar value, which results to a vector with the same direction but with different magnitude. We call these vectors scaled vectors. For example, we can scale vector 2, 3 by 4 and end up with scaled vector 8, 12. So a vector space has three main properties. First, it must be a collection of vectors, which means that every element in the vector space is a vector itself. Second, the vector space must contain the zero vector. And third, it must be closed under addition and scalar multiplication. That means that applying addition or scalar multiplication on elements of a vector space will result in an element that is still part of that vector space. Now there exists a special type of space wherein it's not required to contain the zero vector. We call this space the affine space. Now why is this affine space so significant? Well, having a zero vector in a vector space allows us to perform addition and scalar multiplication with a reference. Since the affine space does not contain the zero vector, and thus has no reference, the affine space is no longer closed under addition or scalar multiplication. So let's look at a few examples on determining vector spaces. Say we have a set of vectors containing all third-degree polynomials. Some elements in this set would be x cubed, 2x cubed, and x cubed plus x squared plus 1. So all polynomials as long as the highest degree is 3. So we ask ourselves, is the set of vectors containing all third-degree polynomials a vector space? Since a vector space must be closed under addition, the sum of any two vectors must also be a third-degree polynomial. And since it is closed under scalar multiplication, scaling any third-degree polynomial must also result in a third-degree polynomial. So first let's look at scaling. Take for example x cubed plus 1. If we scale this by 2, then we end with 2x cubed plus 2. And since the highest degree is still 3, then it is still a part of the set. And if you try this with any other real number, you will find that this set is closed on scalar multiplication. Now we need to test if it is closed under addition. Take for example x cubed plus x cubed. If you taken any basic algebra course, you should know that the answer to this will be 2x cubed, which is still in the set of third-degree polynomials. However, consider adding x cubed plus 1 and negative x cubed plus 1. We end up with 2, which is not a third-degree polynomial. Therefore, this set is not closed under addition and thus is not a vector space. Okay, let's look at another example. Is the set V equals xy such that x plus y equals 1 a vector space? Some vectors contained in the set are 1, 0, 2, -1, and -5, 6. However, we notice that the zero vector, the 0, 0, is not contained in this set, since 0 plus 0 does not equal 1. Therefore, since the set does not contain the zero vector, It is not a vector subspace. So let's quickly touch on the concepts of vector subspaces. A vector subspace is simply a subset of that vector space. It retains all of the vector space's properties, including being closed under vector addition and scalar multiplication. With this in mind, we can conclude that all subspaces are also vector spaces, since they essentially satisfy the properties of a vector space. So vector spaces have a very important application that we take for granted in our everyday lives. Have you ever noticed that when you're on YouTube and all the videos in the recommended section are interesting to you? The same thing happens when shopping online, and it recommends products you may not specifically need, but you know you want. These websites have mastered the art of constantly recommending items specifically for you, the consumer. This recommender system uses what we call vector space models to always recommend items relevant to you. Sites like Amazon, Myntra, and Flipkart all use the system. So here's an example of the equations that the vector space model uses. It's a bit too complicated to go into detail, but you can find many examples of this online. Some other practical yet very complicated applications of vector spaces are design of digital filters, algorithms such as least mean square, recursive least square, minimum mean square error, and zero forcing, as well as the optimization of manifolds. So now we have shown you the conceptual and practical applications of vector spaces, affine spaces, and subspaces. Take this information to heart, become a better person, and change the world.